Hello and welcome back. Today we are going to be talking about finding volumes by cross sections. Well, what does that mean? Well, let's say that I have any object, like here's my stapler, right? If I wanted to find the volume of my stapler, I could actually cut and slice shapes within here and then integrate that information and find out the entire volume, or at least an approximation of it. So if I cut a square slice out of here and I found the volume of that little square, and then use that formula and found, the volume of this one, 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 all those little square slices, added them up, I would actually have the volume of the entire stapler. Again, an approximation. And you can do that with any shape. I could find triangles of this stapler. I could find semicircles of this stapler and get an approximation of the entire volume of the stapler. And you could do it with any object. Here's psi. We could do this with psi. We could find the volume of psi by slicing pieces of psi, and that's his name, psi, C-Y, slicing pieces of him in different shapes, and then integrating that information and finding the entire volume. So there are two ways. Oh gosh, did it freeze? All right, so there are two ways actually to calculate these cross sections. If they are perpendicular to the x-axis, then the volume is going to be with respect to x, integrated a to b. And if it's perpendicular to the y-axis, then that volume is integrated from c to d with respect to y, okay? You'll see that as we do that. But before we dive into actually finding a volume by cross sections, let's take a little reminder here to find out how do we find the area of different shapes, because we're going to be using those when we actually make our slices. So square, we've got, this is probably our easiest one, two sides. The area of a square is equal to s squared. Oh, good. Okay. An equilateral triangle, each side is equal to s. Well, the area of a triangle, you'll remember, is 1/2 base times height. So our height here is going to be equal to radical 3 over 2s. That comes from the, whatever, I don't know how to say it, but the 30, 60, 90 triangle, the formula for a 30, 60, 90 triangle. So the area of this, because this is radical 3 over 2s, and then you'll have here is s, so of an equilateral triangle, it'll be 1/2, nope, not 1/2, whoops, radical 3 over 4, 1/2 times radical 2, or 1 over 2, you get that, s squared, okay? I took like way too long to explain that. An isosceles right triangle, we can actually find that. This is s, this is s, these are 45-degree angles, right? So up here, this was 30, this was 60. So then this is equal to s radical 2, and that's from our standard 45, 45, 90 triangle. So our area here for an isosceles right triangle is going to be 1/2 s squared, right? Base times height. And for a semicircle, we're just going to have the area of a semicircle is equal to 1/2 pi r squared. Okay? So hopefully that helps you to remember and will become useful as you work through some problems. So let's actually work through a problem now. Before we dive into that, I want to show you an image here, and I'll have a copy of this on our Google Classroom notes. So here you can see if we have square cross sections, what these kind of look like, right? We've got a shape here, and we're going to take square cross sections and find the volume of this shape. Well, first we're asked to write the area of one square in terms of the given functions. Well, if this is f of x, this is g of x, we have f of x minus g of x times f of x minus g of x, right? So you can kind of see that. So our area is going to be equal to, can you see this okay? Area is equal to f of x minus g of x quantity squared. And if we add an infinite number of squares, then we get that volume of the solid, right, that we talked about earlier. We add up all of these infinite squares. We only have a few here, but of course they're infinite. Then we can give the volume of that solid. So that would be written as the integral from a to b of f of x minus g of x quantity squared dx. Okay? So taking that integral would give us the volume of this shape. Let's do that 3 more times. Let's do this with semicircles. So we've got the same shape here, but again we have f of x, we have g of x. these are a little bit trickier because we have to be able to use the radius and then write the area for one semicircle. So our radius here, we can just call this r, right? So r is actually going to be equal to 1/2 times f of x minus g of x, which f of x minus g of x is this length right there, right? And so then our area is going to be equal to pi over 2 times 1/2 times f of x minus g of x quantity. Oop, I don't want to square it yet. Sure, now I want to square it. Quantity squared. Okay. Then our area will actually be equal to, because this is squared, so that's 4, 2 times 4 is, so we have pi over 8 times f of x minus g of x squared. Okay. So now how would we find the volume of this entire solid? Well, again, we're going to integrate. So our volume is equal to pi over 8 times the integral from a to b of f of x minus g of x quantity squared with relation to x. All right, I want to do this 2 more times with an isosceles right triangle and with an equilateral triangle. So with our isosceles right triangle, we want to first, like we've been doing before, write the area of the triangle in terms of f of x and g of x. So this is f of x minus g of x, this is f of x minus g of x. They're the same, right, because it's isosceles. So our triangle area is going to be equal to 1/2 the base times the height, which is just f of x minus g of x quantity squared. So then to actually integrate this, our volume is going to be equal to the integral from a to b. This is a, oops, you can't see it. This is a, this is b, in case that wasn't clear earlier. The integral from a to b of 1/2 times f of x minus g of x quantity squared dx. And of course you can pull that 1/2 out if you want. Finally, with our equilateral triangle, we need to know the base and then the height, right? Well, our base, so we have to use the properties of a 30, 60, 90 triangle, which we've talked about before. So our base and our height, this is our height here. I wanted to make it dashed, but then it kind of became solid. So if our base is f of x minus g of x, our height is radical 3 over 2 times f of x minus g of x, right? So then our area is going to be equal to 1/2 base times height, so it's going to be 1/2 times radical 3 over 2, so that's going to be radical 3 over 4 times f of x minus g of x. That's going to be squared. Okay? So then to write the volume as of a solid, then we would have our volume is going to be equal to the integral from a to b of the area of each of those little triangles minus g of x quantity squared dx. Okay? So hopefully that makes sense and help clarifies how we're going to work through this. And I think seeing these pictures as well, which are, of course are much better than I could ever draw, hopefully helps clarify what this really looks like. So let's actually do a problem here. Okay, we want to find the volume of the solid whose base is bounded by the function y equals radical x, x equals 4, and the x-axis. Each cross-section is a square taken perpendicular to the axis. Okay, well, first of all, we're going to just draw our function. This is y equals radical x, right? And we're integrating it. We want to find it. It's bounded by the x-axis. That's going to be here. And x equals 4. So if this is 4, right, 4, 3, 2, 1. This is 4 there. This is where we're going to stop. So we want to find the volume of this solid here with square cross sections, right? So I guess I can write it in green real quick. Like, imagine this is one little square right here, right? And that little square is going to be equal to, it's going to have a base of radical x, right? So the area of a square, you remember, is s squared. But the one side of that square, and in this case, is radical x. So our volume is going to be equal to the integral from 0 to 4 of radical x quantity squared dx. And now we can just integrate as normal. So we have the integral from 0 to 4 of x dx. So that's going to be equal to 1/2 x squared evaluated from 0 to 4. So we're going to have 1/2 times 16 minus 0, which equals 8. That's it. So the volume of the solid created here with a bunch of squares would be 8. Okay, let's do quite a few more examples. I want to make sure that we really understand this. It requires a lot of 3D thinking, so I think it's important to go through as many examples as possible. We want to find the volume of the solid whose base is a region bounded by the circle x squared plus y squared equals 9, with the cross sections taken perpendicular to the x-axis. There are isosceles right triangles with the hypotenuse lying at the base of the circle. Okay, so we've got a lot going on here. First of all, we're doing a circle, right? We have a circle here. X squared plus y squared equals 9, so this is going to be 3, 0. And we're taking these perpendicular to the x-axis, so we're going to have, I don't know why I drew it here when I could have drawn it here, but we're going to have this to this, okay, right? Perpendicular to x-axis. And this height here is y, and this height here is also going to be y, right? They're all going to be the same. And then we want to find, I'm going to erase this because I don't need this space because I used it up with other things. We're going to take and make sure that we have our right triangles drawn correctly. So we have an isosceles right triangle, right? Right. And our isosceles right triangle, the peak of that triangle is going to run right along the x-axis. So this here is going to be y. This is going to be y because the hypotenuse is at the base, right? Y and y. And then our height here, well, this is y radical 2. This is y radical 2. So this will also be y. That's convenient. So the area of our triangle is going to be 1/2 times our base, which is 2y, times our height, which is y. So that's going to just equal y squared. And actually, we know what y squared is. Y squared, well, x squared plus y squared is equal to 9. So y squared is equal to 9 minus x squared. Okay, that's going to be helpful to us. So we're to find our volume, because we're taking this perpendicular to the x-axis, so this needs to be with respect to x. Our volume from 0 to 3, I'm just going to find from here to here, is equal to, you know what? I'm going to erase this. I could find my volume from -3 to 3. But if I find my volume from 0 to 3, then I can just multiply it all by 2. So our volume from 0 to 3 of 9 minus x squared with respect to x dx is equal to, we're going to have 2 times 9x minus 1/3 x cubed, evaluated from 0 to 3. Of course, we're going to get 27 minus, what is this, 9 minus 0 minus 0. So you get 2 times 18, which equals 36. Okay, I think that's a good problem. All right, I'm going to pause for a second. Okay, so we found a circle with respect to x. Let's find something perpendicular to the, well, anyway, sorry, that's not what I want to do yet, but let's just do another example. Let R be the region bounded by the graphs of y equals x squared and x equals 9, or I'm sorry, x equals y squared and x equals 9. Find the volume of the solid that has R as its base if every cross-section by a plane perpendicular to the x-axis is a semicircle. That's what I wanted to do next, was deal with semicircles. So our graph, x equals y squared, right? X equals y squared. So if y is going to be equal to plus or minus radical x. So our graph is just going to be a sideways parabola, right? And we also, this is going to be bounded by 9, x equals 9. Okay? So we want to find a semicircle. If these are a bunch of semicircles, well, the base of our semicircle, this height, this radius is going to be equal to y, right? And this would also be equal to y. I mean, I guess you could say it's equal to negative y, but the length of it, a length cannot be negative, so that's why I'm saying it's y here. So the area of our semicircle is equal to 1/2 times pi r squared. So in this case, it's going to be 1/2 times pi times y squared. Well, y squared is just equal to x, so our area is equal to pi over 2x. Okay? This is perpendicular to the x-axis, so I need to take this with respect to x. So our volume is equal to the integral from 0 to 9, right? I'm starting at 0, I'm going to 9, of pi over 2x dx. So this is just equal to pi over 2 times, looks like 1/2 x squared from 0 to 9. So we're going to have pi over 4 times, what is this, 81 minus 0. So our answer to our volume is 81 pi over 4. Okay? All right, let's do a few more examples here, just 2 more. We want to find the volume of the solid whose base is the region bounded by the lines x plus 2y equals 6, x equals 0, and y equals 0, if the cross sections taken perpendicular to the x-axis are equilateral triangles. Okay? So if I graph this, x plus 2y equals 6. Of course I know how to do that, but I just kind of don't feel like dealing with it right now. So, one second, let me pause quick. Okay, I graphed this on my calculator. I know that's terrible, but I did it anyway. 1, 2, 3, and I think it's at 6. 6. 1, 2, 3, 4, 5, 6. All right, so there's our line. Fluff here on the, and this is what we want. I probably should have drawn this bigger, but this is where we want to find the region bounded here by these lines, and they're going to be perpendicular to the y-axis, equilateral triangles. So finally, we're going to deal with that y-axis. So what's this length right here? Well, that's what we need to find out. This length here is going to be x, right? No matter what, this is x. That's our x-axis. And x is equal to 6 minus 2y, right? So our area is going to be equal to 1/2 times our base, which is 6 minus 2y. Oh, damn it. Sorry, I misspoke there. I want to draw this. I want to draw our equilateral triangle here. Here's our equilateral triangle. This base is 6 minus 2y, right? So we want to find the area. This is, or you could just say this is equal to x. So our height here is radical 3 over 2x, which is going to be equal to radical 3 over 2 times 6 minus 2y. So the area of our equilateral triangle is going to be 1/2 times the base times the height. So 1/2 times radical 3 over 2 times, these are going to be squared, 6 minus 2y squared. Okay? So now I can actually find the volume. Our volume is going to be equal to the integral from, we're going from 0 to 3, okay? We're going from 0 to 3 because these are perpendicular to the y-axis, so we need to go with a dy here. From 0 to 3 of radical 3 over 4 times 6 minus 2y squared dy. So this is going to be equal to, I'm just going to pause it and like do the math, and then if you want, you can check yours. Okay, if you want to see me do all of that, I guess I can demonstrate it in class, but with the power of Mujvi magic, I integrated and I got our volume is 9 radical 3. All right, one last example here. Let R be the region bounded by the graphs of y equals x squared and y equals 2 minus x squared. We want to find the volume of the solid that has R as its base if every cross-section perpendicular to the y-axis is a rectangle of height 3. All right, one moment. I'm going to pause and graph this. Okay, I've graphed it. And I'm here. This is at 0, 2. This is at 1, 1. This is at 0, 0. This is at negative 1, 1. That'll be important for what we're finding out here. And we're actually going to want to do probably 2 sets of integration here, right? It's just going to make life a lot easier. And this is perpendicular to the y-axis, so we're going to need to go from 0 to 1, and then from 1 to 2, okay? So what are our bases here? Well, we're using rectangles. What is a rectangle of height 3? So the area of a rectangle, of course, is equal to base times height, and in this situation, height is equal to 3. Well, what's the base? Our base here, right, is going to be x and x, and our base here is going to be x and x, okay? Well, base 1, on base 1, which I'm going to, this was base 1 here, base 1, y was equal to x squared, so x is equal to the square root of y. And on base 2, this is base 2 here, y is equal to 2 minus x squared. So x is equal to the square root of 2 minus y. And this is what we're going to use here for our areas. So the area 1, which is this one here, or I'm sorry, the bottom one, this is area 1 with base 1, is going to be equal to 3 radical y, right? Or, sorry, 3 times, 2 radical y, because I have 2 x's, right? 3 times 2 radical y, so that equals 6 radical y. And our area of our second base of the top half of this sort of circle-ish thing that we've made here is going to be 3 times 2 radical 2 minus y. So that's going to be equal to 6 radical 2 minus y. Okay? So now we can find our volumes. Our volume is going to be equal to the integral from 0 to 1 of that first base, that first area, which is 6 radical y dy, plus the second volume here, which is going to be the integral from 1 to 2 of this second area, 6 times radical 2 minus y dy. So now we just integrate as usual. I'm going to pause and do that. Okay, I worked through all of that. Hopefully you can see how that happened. The most important part is being able to set this up and see where we got these areas from and where we're going to integrate from. The rest is just simple integration, which you're very familiar with. If you have comments or questions, leave them in the comments below. I look forward to seeing you in class. Have a great day. Bye.